Good afternoon. My name is Ben Levitt, and I'd like to thank the InnovaCon community, Laszlo, and Brett for the opportunity to present today. Today's topic is a favorite of mine, the econometrics of MBSE. I'm presenting today from Cambridge, Massachusetts, representing my firm, Technology Strategy Partners, a boutique system engineering and system architecture consultancy founded out of MIT. For interest, the F-35 Joint Strike Fighter is one of our favorite examples. One, because there was a base case for the MIT commonality study, and two, it's an amazing example of the occurrence of platform divergence and the importance of system engineering management, that is incentives, management levers, and of course, understanding and managing the technical complexity. I started my career at Raytheon in 2004, and my experiences there have been the foundation of my technical and systems journey. I've led conceptual innovation in the Think Lab environment, utilized machine learning, and managed the system requirements and architecture of a missile defense system. I've had the privilege to live the full product lifecycle, and that's highlighted by my experience below. My functional roles are represented in solid lines, and sub-roles are as dotted lines. After a brief stint at MIT for graduate school, I joined TSP in 2016. Today, I lead transformational projects for aerospace, automotive, and tech firms. When I see the word complexity, my mind immediately jumps to systems engineering. This DARPA plot on the growing complexity, to me, is really an opportunity for engineers to use their strengths as system thinkers to better products and ecosystems. DARPA sees a worrisome trend. I see an system engineering opportunity. Before we dive into the details of the business model, let's unpack the differences between traditional system engineering and model-based systems engineering. First, system engineering is often defined as process, rigor, and dispersed models and data. The main goal of system engineering is reducing late defects and limiting the risk of interface and informational conflicts. As systems grow and complexity grows with it, these goals become more and more difficult. When I think of model-based system engineering, I think about moving some of that process and the paperwork that goes along with it into a model environment. So I see unifying models at macro and micro levels constituting a single source of information. And most important to me, in my experience, is the direct connection between system requirements, design, and system validation. I'd like to start a discussion today by walking you through a real-life scenario. This case highlights the conflicts that managers and engineers face when starting an MBSE project. And it really motivates the need for business modeling for MBSE initiatives. An aerospace company called Mars XYZ is about to begin the development of a new program. As you all can relate, there's intense cost and schedule pressure, and MBSE has been chosen as a likely candidate to expedite the program forward. Mars XYZ has three main goals as it pertains to MBSE. Conduct early cross-functional trades, identify interfaces, and verify requirements in later phases of the program. Mars XYZ is structured as a matrix organization. Our key stakeholders listed here traverse the product lifecycle: front-end system engineering, hardware and software design teams, tests, as it is verification and validation, and two program teams. Program A, the previously mentioned program that is a focus of this new product, and Program B, which is a subsequent adjacent program. The dynamic between the two programs will be clear later in the scenario, but I wanted to just mention it here. I've also included this plot to highlight the staffing profiles for these functions across the life cycle. Each stakeholder has diverse but positive expectations on the performance of the model. I've listed a few here, but the main theme is that each function expects the world. For example, the software team expects improved requirements, the test team expects a complete model, and of course the system teams expect that the model will create a better systems environment, create and a better systems product. And the program teams expect a reduction in risk to both their cost and schedule. Now, that's well said, and those are typically the expectations for all MBSE programs. But when we take a step further into this, we start looking at budget and resource expectations. Things are quite different across the board. MBSE is often viewed as a front-end activity, paid for and created by the systems teams. While this is somewhat true, it misses the need for maintenance during development and the impact that has to the MBSE and to the models when the validation team starts validating the system. In addition, program managers expect to see immediate payback despite the organizational transformations that typically follow large initiatives like MBSE. So the question always comes up as, the question XYZ is asking right now is, how would you recommend funding this model? Is systems going to pay for it? Is validation going to pay for it because they benefit the most? Are the programs going to benefit? Are the programs going to fund it even though they may not benefit immediately from it? What practices would you suggest incentivize cooperation on the model? My hope is that the Mars XYZ case hits a pain point for you when you're trying to navigate the organizational funding process for MBSE. Our challenge today is to understand the econometrics of MBSE, and this is where it gets personal for me, because these are the questions I consistently hear. What are the dynamics of the ROI? How do I encourage managers to invest in MBSE? And how do we plan funding across the program lifecycle? I'm going to start with the results today and peel back layers one by one. So the main takeaway. The main takeaway is that payback is not likely in the first installment of MBSE. This is due to the impact of the initial investment, the learning curve, and the adaptation of MBSE processes. Managers can expect better outcomes on subsequent MBSE programs, driven primarily from an established model, but also best practices and an adequately trained team. So what are we looking at here? So we have 4 key KPIs. Net present value, FTEs, basically resources, duration, schedule, and rework. A few aspects here that I want to point out. First, rework is the only consistently positive metric in the first installment. We see highs and lows, but that's the one metric that we always see as a positive. Second, the first program may not produce the results expected during the investment period. And this emphasizes our Mars XYZ scenario where all stakeholders expect immediate results and results on the first installment of MBSE. What scares me is that this opens the door for canceled or altered MBSE programs based on the perception of failure because the first program doesn't produce a positive NPV. Traditional models typically miss the mark for estimating system-level transformation because they do not include enough of the dynamics. We've included several key factors here to adequately understand the major and minor effects of the MBSE inclusion. A few that I want to point out. Product quality, so that's defect and rework. And productivity is amount of scope executable per person per unit time, basically their efficiency. Graphically, I represent all these inputs as a system dynamics plot. where you can see directional impact to scope, resources, productivity, and rework. There's actually a funny guideline not to include dynamic plots and presentations, but I have a feeling that this is the right group for that, a right group to break that rule.
Next, I'm going to walk through how we frame the problem space and why we're using 4 discrete scenarios. The first scenario is called planned. This is an as-planned project, which isolates the effects of rework and scope creep to act as a reference point. We're using this because MBSE has a prominent effect on those attributes, quality, rework, and scope changes, and this planned isolates those effects from the more realistic scenarios. One of those is a baseline scenario. This is similar to what we would usually bid for a project, a framed scope with a realistic factor for issues. Next is the first application of MBSE. Here we can expect higher initial investment, stronger growing pains, and some MBSE potential, but those that are not fully exploited. One of the key concerns of the MBSE transition is your overall cultural resistance. The team is embracing a lot of growing pains in this first MBSE trial. There are ways to ramp up faster, such as training the core team on MBSE usage, using SysML and UML language ahead of time, and providing an MBSE hotline service for real-time issues. Last is the subsequent, or in other words, an established MBSE program. This case integrates an appropriate set of best practices and an adequately trained team who can champion MBSE in the organization. We should note that recurring costs of MBSE maintenance and some extra efforts are still on the table here. We would also expect a shift to a more agile development process, this including phase gates, to fully take advantage of the model. And we're using each one of these phases to adequately show the differences between the plan, the current traditional system engineering, and what MBSE looks like as you are integrating it into your organization.
So let's further unpack the results. On this plot, the y-axis is FTEs and the x-axis is time. A few key observations. Number one, the planned scenario is quite unrealistic. Number two, the baseline is basically a shift of that plan with rework included. And you can see that based on the slight curve at the end of the program. Next, the first MBSE includes quite a large investment period. And that's a huge contributor to our negative NPV in the early stages of the MBSE program. Typically, this is a very difficult hurdle for managers to overcome. Now let's focus on the subsequent programs, the dark dotted line. So we see the standard curve without the the large upfront costs. This is the curve and dynamic expected by managers when they initially approve an MBSE initiative. So more resources front-loaded, efficiencies taken from increased iteration and collaboration. On the right, we have a different display of the same dynamic, and we've broken it out to include planning, design, fixed costs, rework, system engineering, test, and documentation. And what I love about this chart is the rework. And the rework is in orange. And you can see the baseline of first MBSE rework is, for the most part, a normal curve that crosses the entire life cycle. When we look at subsequent MBSE, we see rework is pushed forward, so more upfront or front-loaded is another way to say it, in the project. And since that is one of the goals of system engineering, to reduce latent defects, I love to see that. I love seeing MBSE work in that fashion. Now let's unpack the MBSC effect on FTE loading and overall staffing. On the left side is the cumulative growth of FTEs during the program. So this is for planning staffing. And two interesting notes of interest. Number one, baseline and first MBSC are relatively similar from a loading perspective, with the first MBSC case slightly more front-loaded, and we can understand that based on that investment period. Next, the plan, the theoretical, one that did not seem realistic, is actually quite similar to our subsequent MBSC, our established MBSC program. And that's quite impressive and amazing if you think that using MBSC effectively can create what we would typically do with a traditional system engineering program without defects, without the big rework addition. Next, on the right side, we see cumulative growth relative to baseline. So this highlights the delta between the two development methods. Again, we see the difference between the first and subsequent programs and how the cost savings from the first MBSC are quite limited by the number of things we've mentioned before: learning curve, initial investments, and adapting MBSC processes. And I'm just going to make a note here that these curves do not affect the post-delivery effects of MBSC, or they do not reflect those effects. And you can argue that there's a stimulus and there's a competitive advantage about doing things with a higher quality and faster. And that should lead to more contracts. And those things are hard to model. They're not included here. To conclude today, I'd like to take a moment to discuss what current estimation methods miss the mark for MBSC initiatives. Gantt charts, usually seen in Microsoft Project, work well for discrete tasks with our historical metrics, but create difficulty with continuous transformation, such as an organizational shift. We have seen estimates primarily driven by a single team, typically systems teams, that only consider their budget or their respective program's budget. It's also difficult to estimate the effect of an agile transformation, not to mention the learning curve and the organizational best practices that are included with them. I'd like to leave you with a few takeaways today. Number one, the benefits of MBSC are often delayed as the model and organizational change typically outweigh the heavy investments in terms of time and schedule. We argue that the long-term effects of MBSC are strong enough to outweigh these growing pains and are worth the time to wait for the learning curve and the best practices to be instituted. And third, organizational change is not easy. And I continue to reiterate that managers are the key driver for a successful MBSC program. Thank you for your time today, and I'm happy to answer your questions.